In 6.4, we were talking about the sampling distribution, and that's what we're going to continue on in 6.5. Now, an X distribution is a probability distribution. X means one value, one person, one item. The X bar distribution is a sampling distribution, which means we have a group of means or X bars. And what we had looked at the end of 6.4 were that the average of the sampling distribution is going to be equivalent to the average of the X values. The standard deviation of the sampling distribution is equal to the standard deviation of the X values divided by the square root of n. And then the z, when we have to calculate the z value, it's x bar minus mu, which is the same, but now the denominator is sigma divided by the square root of n. Now, what you have to recognize is, now, when do I use the z that's x minus mu divided by sigma, or x bar minus mu divided by sigma divided by the square root of n? And it's all as to whether you're talking about one item or multiple items. So, let's start looking at some examples. All right, it says the manufacturer of a new compact car claims the miles per gallon for the gas consumption is normally distributed. Okay, that's important. It means we can use the Z table, so it's normally distributed. We have a mean of 25.9 miles per gallon and a standard deviation of 9.5 miles per gallon. 30 cars are tested. Okay, so what we know is that mu is 25.9. I know sigma is 9.5, and then 30 cars are tested, so n equals 30. So I have more than one car, so this is the sampling distribution, okay? N equals 30. So if you'll notice over here, it says the probability that X bar. When I see that X bar, I know I'm talking about a sampling distribution. So when I go to calculate Z, I have to do X bar, 23, minus mu, 25.9, divided by sigma, 9.5 divided by the square root of 30. Now the reason I have to do that is because this is a sampling distribution, or X bar. Now you can put all of this into your calculator and only hit equals once. The key is knowing where to put your parentheses. So I'm going to try to get my calculator up here so you can see. All right, so you're going to do open parentheses 23 minus 25.9 close parentheses divided by, and then it's extremely important, open parentheses 9.5 divided by the square root is second x squared, and then my calculator automatically opens a parentheses for under the radical, and I'm putting in 30. Whoops, not 30 points, sorry, 30. Then I'm going to close the parenthesis under the radical, and then I'm going to close the denominator and then push equals. And I get negative 1.671995, but we're talking about a z value, so we always round to 2 decimal places. So it gives me negative 1.67. This is a less than, so I just go to my table and find negative 1.67, and I'm not going to put that up because hopefully by now you can read your table, and you find 0.0475. 0.0475. So the probability that a sample of 30 cars has an average of less than 23 miles per gallon is 0.0475. Now, how would this differ if you were talking about one car? See, here we're talking about the average of one car has less than 23 miles per gallon. Here we're talking about the average of 30 cars having less than 23 miles per gallon. Well, the difference is over here, your Z would be calculated by 23 minus 25.9 8.9 divided by just 9.5. So your z value, when you calculate that, you calculate negative 0.31. So if you went to the table and found negative 0.31, you get 0.3783. And this is the difference of 1 car's probability, the average of 30 cars' probability. Now, down here we have in between, and it's still x bar, so we're using the sampling distribution. So I have to find the z value for 23, which we just did above, 23 minus 25.9 divided by 9.5 divided by the square root of 30. We already found that to be negative 1.67. Then I have to find a second one, which would be 28 minus 25.9 divided by 9.5 divided by the square root of 30. So, again, the key is knowing where your parentheses go. I'll try to do that again where the calculator's up there. I know it's not the greatest scenario because of the lighting, so I apologize. So, open parentheses. 28 minus 25.9, whoops, close parentheses, divided by, open parentheses, 9.5 divided by the square root of 30, close the square root, close the denominator, hit equals. You get 1.210 or 1.21. Now, since the sampling distribution is between, that means we need to find these probabilities and subtract them. Well, we already found the probability at 1.67. That was 0.0475. And now I'm going to go to the table and look up 1.21 and find 0.8869. So to find the probability that x bar is between these two, you take these two values and you subtract them, and you get 0.8394. 0.8394. Okay. We're going to do some more examples. So if you'll go to the next page. Now, it talks about what is called the central limit theorem, and that basically says that if the problem is stated that it's normally distributed, then you're fine. Don't worry about anything. If it doesn't state that, then your n has to be a number that's 30 or larger before you can use the probability z-table. So in essence, that's always going to occur. Because if you'll notice in this first one, it says response time for a fire department is mound-shaped with mu of 8.8 minutes and sigma of 2.1 minutes. Well, mound-shaped right there tells me it's symmetrical. But even if it hadn't, I'm okay because my sample is larger than 30. It is 32. So we know mu is 8.8, sigma is 2.1, and then sample that tells me n is equal to 32, okay? All right, so it says, what is the probability that x bar, so this is a sampling distribution, so I know when I calculate z, I'm going to do x bar minus mu divided by sigma divided by the square root of n. And when you go to your calculator, just again, be sure you put the parentheses in the correct place. And when you calculate that, you should calculate that to be 0.54. Now, this is a less than statement, okay? So that means I just go to 0.54 on the table and use that number. So I'm looking for 0.54 on the table, and when I do, I find 0.7054. And again, this number 7054 comes from your Z table. Now, be careful if they ever put the probability kind of what we would call backwards. This would be rewritten as the probability of X bar, and since the mouth is open to the X bar, I would switch the inequality. So this is a greater than, so I know I'm going to do 1 minus the number from the table. But before I can find the number from the table, I have to calculate my Z, and it's a sampling distribution. So my Z will be calculated as 8 minus 8.8 divided by 2.1 divided by the square root of 32. And when you put that into your calculator, you should calculate negative 2.15. Then I'm going to go to my table and locate the probability on the Z table at negative 2.15, and I find 0.0158. And then when you subtract 1 minus that, you'll get 0.9842. All right. Look at this next one. X is normally distributed. Now that's important because our sample is only 10. So anytime your sample is under 30, it needs to be sure and say that it is normally distributed. Now notice A and B both are less than, and they are both 13.2. The difference is this is X bar, which is your sampling distribution. This is X, which means one person, one item, and that would just be a normal probability distribution. Where is that affected? All in how you calculate the Z. Here we would calculate Z, 13.2 minus 14 divided by 3.4, where over here we would calculate it as, divided by the square root of 10. About messed up there, sorry. This is the sampling distribution, so I have to do divided by the square root of n. Over here, I'll do 13.2 minus 14 just divided by 3.4. So what happens is it's different in your calculation of your Z value. For the first one, this one, when you calculate your Z value, you're going to calculate negative 0.74, whereas when you're talking about one person or one item, you're going to calculate it as to be negative 0.24. So that completely changes the probability. So if you go to the Z table and you look up negative 0.74, and this is a less than, so I just have to go to the table and use that number, I get 0.2296. So the probability that an average of 10 people or items is less than 13.2 is 0.2296, whereas one person or item is less than 13.2. Go to your Z table, locate negative 0.24, and you find 0.4052. So it completely changes the answer depending upon if you're talking about an X value or an X bar value. Now, I want to look at some examples that will be what you'll see on assignments and tests because it's important you understand the wording here. So suppose it is known the time spent by customers in a McBurger's fast food restaurant is normally distributed, so that's good, it doesn't matter what size my N is, has a mean of 24 minutes and a standard deviation of 6 minutes. Find the probability an individual customer, one person will spend more than 25 minutes. Because it says one person, this means that X is greater than 25 minutes. And that's important because then that dictates how I calculate my Z. It will be 25 minus 24 divided by 6. So when you calculate that, you get 0.1666666. So what we're going to do is round that to 2 decimal places. So you get 0.17. This is a greater than, so I do 1 minus the number from the table. So I go to the table and look up 0.17 and I find 0.5675. Do that subtraction and we get 0.4325. So this is the probability that one person spends more than 25 minutes in the restaurant. Now, part B is worded differently, and this is what you have to be careful of. Now they're talking about a sample of 36 customers have a mean of more than 25 minutes. So this will be X bar because we're talking about 36 customers more than 25. So the probability looks the same other than this is X and X bar, but the way you calculate Z changes. So this would be 25 minus 24 divided by 6 divided by the square root of 36. And when you calculate that, you get 1 or 1.00. So that's your Z value. So now I have a greater than. So I do 1 minus, I go to the table, the Z table, and look up 1.00 and find 0.8413. Do that subtraction, and you get 0.1587. So this is the probability one person will spend more than 25 minutes in the restaurant. This is the probability that 36 customers will average more than 25 minutes. So it significantly drops. Then in part C, it changes into 100. So we're still finding the probability, but now that the average of 100 people spend more than 25 minutes in there. So when I calculate Z, I now have 25 minus 24 divided by 6 divided by the square root of 100. And you do that calculation and you get 1.67. It's a greater than, so I'm going to do 1 minus the number from the table. Go to the table and locate 1.67, and you find the probability to be 0.9525. So we're going to do that subtraction and get 0.0475. So the big thing is knowing if you're talking about one person or one item or multiple, because that dictates the Z that you're going to use to calculate. All right, I want to look at this example. A soft drink machine is regulated so that the amount of drink dispensed is normally distributed, so that's important, so I know I can use the Z table. It has a mean of 7 ounces, so I've put that here. Standard deviation of 0.5. Periodically, the machine is checked by taking a sample of 9, that's where I get 9, and calculating the average content. The mean of the 9 cups falls with, if the mean of the 9 drinks falls within 2 standard deviations, the machine is said to be operating okay. If not, actions would need to be taken. So what action should take if a sample of 9, so there's n equals 9, has a mean content of 7.4. Okay, here's where you need to be careful. This mean of 7.4 refers back to the 9 drinks. So this mean is a sample statistic. So that is X bar equals 7.4. Now, this is talking about standard deviations. Well, Z values are standard deviations. So it needs to fall within 2 standard deviations. So that tells me that my Z needs to be a number 2 or less. So all we have to do is calculate the Z value. So Z equals X bar, 7.4 minus mu, which is 7, divided by sigma, 0.5, divided by the square root of n, because we're referring to that sample of 9. And when you calculate this, your Z value is 2.4. Well, Z value tells you how many standard deviations away that you are. The problem told us we need to be within 2 standard deviations. Well, we're further than 2 standard deviations. We're 2.4 standard deviations. So that tells me that the machine is a little out of whack and needs to be adjusted. That is chapter 6.5.